Hello, and thank you for coming to my talk, and thank you to Black Hat for having me and allowing me to speak. My talk today is going to be about the control flow integrity mitigations on Windows, specifically why they're important, what they do, but most importantly, taking a look at the implementations of these mitigations in kernel mode as opposed to their user mode counterparts. So a little bit about myself. My name is Connor McGarr. I am a software engineer at a security startup called Prelude. And I'm just primarily interested in anything related to Windows internals, exploits, mitigations, hypervisors, all the typical fun stuff. So before talking about what CFI actually is, it's probably worth taking a look at what is CFI aiming to address. Well, most exploits today that want to execute some sort of unsigned code typically need two things. That is, firstly, the ability to coerce a given exploit target to exercise a code path that it might not otherwise exploit. And then using that same primitive, the ability to load data into an exploit target and have the OS or application treat that data as code. And so CFI is attempting to address this first tenet of exploitation, which is verifying and mitigating any attempts to alter the legitimate control flow of an exploit target. So the canonical example of this in Windows is Control Flow Guard. It's been around since Windows 8.1 in user mode. And this is Microsoft's implementation of a forwards edge CFI mitigation. So this is protecting against indirect calls and jumps. And the way that CFG works is that at compile time, all of the known indirect call targets are stored in a bitmap. And that bitmap is read-only, and it is a per process bitmap. And any time an indirect call or jump happens, we first go to the bitmap to get more information about the call target we're about to invoke. So for our intents and purposes, really CFG, the bitmap states are this is allowed or this is not allowed. The way that manifests itself is a little bit different because there's some memory manager optimizations that are made to the bitmap to compress its size. And depending on how the compiler generates call target boundaries, we need 2 bits really to denote this. But for our intents and purposes, as I mentioned, it's allowed or it's not allowed. And so here's a kind of before and after of the CFG days before. So we have an exploit, in this case, let's say it's a C++ or some kind of browser as an example. There's a virtual function table associated with an object, and there's a list of functions. Well, an attacker with a read-write primitive can locate that virtual function table, overwrite one of the entries, and then coerce the application to actually call that function. Well, in this case, obviously, instead of calling the legitimate call target, we call into ROP gadget or stack pivot or some other deviation of control flow. And so in the after CFG days, everything about the exploitation remains, but instead of just arbitrarily calling whatever we were told to call, we first go, hey, let's go check with CFG. Let's use the call target's address as an index into the bitmap, get the associated bit state, and see if we should actually make this call or if we should terminate the process. So we can see CFG, it does have an effect on exploitation, but attackers do what attackers do, and that is they take the path of least resistance. Why would I mess with CFG and try to find every way to bypass its implementation? Instead of doing that, look for some other way to transfer control flow that is not protected by CFG. Well, one obvious one comes to mind, that's return addresses on the stack. You have a list of return addresses on the stack, a function unwinds, and then eventually that return address is picked up and we deviate somewhere in memory. Well, Microsoft knew about this, obviously, since the beginning, even when CFG was being developed, and they produced a software-based implementation of this called Return Flow Guard, but it was deprecated because of some discoveries by their internal red team, which effectively the source of truth for this mitigation could more or less be deterministically leaked. And Microsoft did the correct thing, in my opinion, again, not that anyone cares, and they said, hey, we know we can't do this in software. Let's do the right thing and wait for a hardware-based mitigation to come to fruition. And Intel's implementation of this is called Control Flow Enforcement Technology, specifically their shadow stack. But Windows also has support for the AMD shadow stack feature. And it's been in user mode since Windows 10 1903. And with CET, again, this is a hardware mitigation, so we need newer processors. And these processors have a new architectural register, the shadow stack pointer, or SSP. And the shadow stack pointer cannot be encoded in a memory operation as the source or destination. And for specifically user mode CET, there's a special write user mode shadow stack instruction, which can only be executed when the processor is running at current privilege level 0 or kernel mode. So it's undefined in user mode. So for all intents and purposes, the shadow stack is completely immutable to a user mode attacker. And anytime a call occurs, instead of just updating the instruction pointer and pushing a return address onto the stack, we now push a return address onto this immutable shadow stack. And anytime a return occurs, we pop the in-scope return addresses of both the shadow stack and the regular stack, and we compare them. If they mismatch, the CPU issues a special interrupt. So obviously, these mitigations are doing a lot to thwart exploitation, but you may have noticed a few things so far. And that is both of these rely on a given source of truth. So as an example, user mode CET and user mode CFG are protected by the user kernel security boundary. If you want to write to the shadow stack, you either need some way to ask the kernel to make it writable, or have some primitive where you can execute that special opcode while the processor is running in kernel mode. And same with the bitmap. You need some way to actually make it writable. This is usually done through a system call. Well, if you have some way to execute code to do this in the first place, obviously these mitigations are non-starters for you. So we have the user kernel security boundary. But the problem is, if you try to implement this mitigation against a kernel mode attacker, but the mitigation itself is in the same privilege boundary as the attacker you're defending against, obviously you're not going to have a good time with your mitigation. An example of this is a kernel mode exploit. We run in user mode, but we have an arbitrary read-write in kernel mode. And everything about the exploitation remains the same. We locate some list of functions in memory, we corrupt it with our own call target, and then we coerce the kernel to actually execute that in-scope corrupted call target. We just have to add 2 more steps. And that is, we just simply use our primitive to locate the bitmap in kernel mode. We then locate its associated page table entry, which is a special structure that is used to map physical to virtual memory. And it contains special control bits, such as, is this a copy on write page? Is it dirty? Is it has it been accessed before? Is it kernel? Is it valid? Is it writable? Is it executable? And one of those things is obviously, as I mentioned, writable. So what's stopping us from locating the PTE, which is stored in kernel mode, marking the bitmap as writable, then just corrupting the bitmap to mark our ROP gadget as valid call target? Our exploitation only requires 2 additional steps if we implement this mitigation in the same privilege boundary as the attacker. Well, luckily for us, there actually is a higher security boundary that we have on Windows, and that is the Windows Hypervisor Hyper-V. And so it's been a while now, but Microsoft implemented a suite of features under the umbrella term virtualization-based security, and this provides a mechanism to guarantee the sources of truth for things like CFG and CET. So the way that VBS works is it leverages second level or second layer address translation or nested page tables. And what that actually does is VMs are in an isolated region of physical memory. So VM1 and VM2, they access what they think is physical address 1000. But there's only one physical address 1000 on the actual machine. So VMs just access memory in context of the VM, and there's a secondary mechanism which performs a final level of translation to say, hey, that memory you think you're accessing, it's actually over here at this system physical memory. So using this, we can actually break out the operating system into 2 what's called virtual trust levels or VTLs, which are effectively VMs in the sense that these are isolated regions of physical memory. So we have VTL 0. This is our normal world. This is typical NT kernel, page tables, the Windows that we all know and love. And now we have secure world or VTL 1. And it's called secure world not because it's inherently secure, but because it is allowed to impose its will on the security policies of VTL 0. So an example that we'll walk through here is something called kernel data protection, which is a newer mitigation under virtualization-based security, which effectively guarantees a region of memory in VTL 0, which is where normal Windows operates, always remains read-only regardless of an attacker has a kernel mode read-write primitive. So again, we have a kernel exploit here. We're running in user mode, and we leak the associated memory of a KDP protected region of memory. We locate its associated page table, and we mark it as writable. So now we actually go to do the write operation. But in this case, where is the write operation happening? In VTL0, which is a guest, like a VM. And so that memory access is then delegated to the hypervisor, which performs the additional level of translation. Well, what KDP does is it sets a read-only slat entry for VTL0 saying, actually, this page is read-only. And those are manifest through the extended page table entries that only the hypervisor has access to. So in this case, even though a kernel mode attacker marks the PTE, which is managed by the regular kernel, as writable, the extended page table entry is the final source of truth, which says read-only. And so this is effectively the same as writing to a read-only region of memory, and what's called a EPT violation or an extended page table violation will occur, and the machine will crash. So as you can see, we actually have ways to guarantee the integrity of the memory in VTL0, the traditional kernel, and what a normal user interacts with. But it's not as simple as just going, okay, take everything we have in the user mode implementations and just shove them in kernel mode and add some hypervisor stuff in there. Engineers have to think about things. An example of this is VM exit. So your processor is running in context of a guest. The guest then invokes the services of the hypervisor, kind of like a system call. Well, the processor then goes to run in VMM mode or hypervisor mode. And that incurs a context switch where the processor has to update its state and a bunch of other things. Well, that's not a free operation by any means. So just the sheer fact that requesting the services of the hypervisor can invoke a VM exit, that's something we have to keep in mind. So with that, let's take a look now at the kernel mode implementations of these mitigations. So right off the bat, we can see that kernel mode CFG, it came around in Windows 10 Redstone 2, which I believe was 2017, a couple additions into Windows 10. So user mode CFG comes in Windows 8.1 as an optional update. We take a lot longer to get the kernel mode implementation. And KCFG is only fully enabled when another feature of virtualization-based security, which probably most of us have at least heard before, Hypervisor-Protected Code Integrity, or HVCI, is enabled. So only when that is enabled is kernel CFG fully enabled. And HVCI works very similarly to KDP in the sense that it tries to guarantee the integrity of memory in VTL0. But what it is looking at is pages which are designated as code becoming data pages, or data pages becoming code. Those are two prerequisites for unsigned code. If you have a code page, that's probably readable, executable. If you want to manipulate the contents, it needs to be writable. If you have a page that's writable, and you want to execute it, it needs to become code. That's what HVCI is looking at. So what happens here is the NT kernel is still responsible for designating where the kernel mode CFG bitmap is going to reside. And there is only one kernel mode CFG bitmap. So every process has its own CFG bitmap, but the kernel mode address space is shared. And so there's 1 2 terabyte region of memory, which is the kernel mode CFG bitmap that all of the images share. The NT kernel is responsible on kernel initialization for determining where this is going to live, and it enlightens the secure kernel through a mechanism called a secure system call, because again, these are isolated regions of physical memory, the regular kernel and the secure kernel. They don't know about the layout of each other. So this secure system call occurs over the hypercall interface. So VTL0 or NT asks the hypervisor, hey, send this request to the secure kernel as an example. And so on initialization, the secure kernel tracks that region of memory associated with the bitmap through an NT address range or normal address range or NAR structure. And this NAR structure is what allows the secure kernel to denote, hey, I know this region of memory is important and it resides in the regular kernel and I need to manage it. Typically, this comes through every kernel mode load image results in a NAR, post-bootloaded drivers, being created, which contains the range of memory associated with all of the executable code of that image. But we also have special items which are not directly tied to a kernel mode image, such as the CFG bitmap or the shadow stacks. So those are regions of memory the secure kernel needs to know about, and they get what is called static NARs. So after the secure kernel receives where the bitmap is going to reside, the following steps happen on every subsequent image load. So every kernel mode load image that happens, that is compiled into CFG support, a new allocation is going to occur from the bitmap range. Now, obviously, we could not commit 2 terabytes of memory at once. That would exhaust the commit limit, and most PCs don't support this. So one of the optimizations that's made is 2 terabytes are reserved, and then on-demand allocations are made as images are subsequently loaded. And what happens is that allocation is then marked as read-only in the slat table for VTL0. So again, even an attacker with kernel mode read-write privileges in VTL0, they can mark the page table entry writable, but it's not actually writable because the hypervisor is responsible for setting the read-only slat entry. And then additionally, the associated bit states are updated in the new allocation to say, here are the indirect call targets that I care about tracking. And in this case, I'm using the source point JTAG debugger in order to debug the secure kernel, and we can see a hypercall is happening in the screenshot here with the mask of GPA, which is guest physical address readable, thus marking the read-only slat entry. That's not the only case we need to care about, the bitmap. So consider, for example, a call to get proc address in user mode. You provide a string, and the exported function address is returned back to you. Well, presumably, you're going to call that memory. Well, that's going to be invoked, since it's through a function pointer, as an indirect call. And indirect calls are checked by CFG. Well, that call target, which you resolved through get proc address, was not known at compile time, so it's not a valid call target. So the point here is that the kernel mode implementation of get proc address is called get system routine. And if you call this, the call target is automatically marked as valid in the bitmap, which is something interesting. I haven't talked much about exploitation at this point, but one of the known weaknesses of CFG is the fact that it is a coarse-grained CFI mitigation. What that means is CFG does not actually validate the call target you're invoking is the developer intended call target. What it does is it takes the address of the call target, looks it up in the bitmap, and if it's valid, it jumps for execution. Well, since the entire CFG bitmap is shared by all the kernel mode images, nothing is stopping us from, example, overriding a call target in Win32K as part of an indirect call with another valid call target from NT or NTFS or somewhere else. So obviously, you can still call into other functions. Well, Microsoft knew about this from the beginning, and they eventually came to the solution of Extended Control Flow Guard, or XFG. And XFG works at compile time. It creates a hash of the function's prototype, so a number of parameters, parameter types, return value, and return type. That information should theoretically be unique to a given function, and that is placed above every call target. And then when an indirect call happens, we take the in-scope XFG hash and we compare that with the expected hash. And if they mismatch, we have a CFG violation. Well, unfortunately, although this takes everything being a valid call target to only developer-intended targets, this was deprecated, although it did have user mode and kernel mode support, and so it's no longer in use. So where does this leave kernel CFG? Well, there's no XFG, and it works just like normal CFG. Some of the mechanics are slightly different because of the fact that there is a new feature in Windows called hot patching. And what this means is, instead of invoking the dispatch function through an indirect call, it's actually fixed up to a new dispatch function, which is highlighted in red here, and it's made through a direct call. There's a little more nuance to it, but for our purposes, this is worth calling out. Another interesting note is that kernel CFG acts as a software SMEP, or supervisor mode execution prevention. So back in the day, what kernel mode attackers would do is allocate some user mode memory, use a read-write primitive in the kernel to corrupt a function pointer with that user mode memory, and then coerce the kernel to actually call that corrupted function pointer, which redirects execution into user mode. The only problem here is the processor is still running in context of the kernel, so the user mode memory is executed with kernel mode privileges. This was a situation of the mitigation itself was implemented in the same privilege boundary as an attacker. The page table entry has a special user supervisor bit, which lets us know what's a user page, what's a supervisor page. So KCFG, even with HVCI disabled, will be a full no operation, except for one single case, and that is a bitwise test on the address. And if it's a user mode address, we still crash the machine even without HVCI being enabled. And one of the other things that attackers know is that the imports address table is explicitly called out in the documentation for CFG as not being protected. So in this case, we have a kernel mode exploit again, and we're running in user mode. We have a kernel mode read-write primitive. We locate the imports table associated with driver.sys, and in this case, we corrupt the PTE to mark it as writable. Now you may be thinking, well, HVCI should be there. How can you corrupt these page tables? Again, HVCI is looking for code becoming data or data becoming code. The imports table is a data region of memory that is simply becoming writable. So HVCI does not care about this. We corrupt the imports entry with ROP gadget, and then we coerce the kernel to invoke this import. So in this case, we call xallocate_pool2, which will do a memory fetch to the IAT and pick up what it thinks is xallocate_pool2, but is actually ROP gadget. And thus, we invoke ROP gadget even with CFG enabled. So you can actually combine kernel CFG with a lesser known mitigation that's not directly related to it called retpoline. And retpoline aimed to mitigate a CPU branch prediction vulnerability called Spectre Type 2. Well, newer CPUs can defend against this, and so retpoline, it isn't really used or talked about much anymore. But one of the things that retpoline did for our intents and purposes is, obviously it does a lot, but it actually patches, or fixes up, I should say, all of the indirect calls to the imports table and makes them direct calls. And it makes those direct calls to a special retpoline dispatch function. But in 99% of cases, an additional feature called imports optimization actually results in this just calling the imports table directly. We can see this in the screenshot here. In this case, the call from NTFS is going to NTZWClose, but it's not being invoked indirectly, it's made through a relative call, or excuse me, a direct call. And even though newer CPUs don't use retpoline, all of the current Windows images are still compiled for retpoline support. So you get the imports being fixed up to direct. And one of the interesting things that I'd like to call out is how this was implemented. There's a feature called Dynamic Value Relocation Table, or DVRT. Back in the day, I think it was Windows 10 1607, the static addresses for the paging structures, like the PFN database, the PTE database, were finally randomized. And the way that this was achieved was through this special feature that was created with support from security and compiler teams, that you can actually relocate a fully static value to some other value, which allowed the randomization to occur. Retpoline used an extension of DVRT, which allowed all of this fixing up to occur, which I think is pretty interesting. So what this means for us is that we no longer have to read from the imports table. So in this case, I wrote a driver for the purposes of this conference talk, and it's called Not Vulnerable Driver. And there's one single call that's made to xallocate_pool2 through the imports table. But you can see in the debugger in the R10 register, I've already corrupted this entry with an arbitrary read-write primitive to 41414141. If we did not have retpoline support, we would have simply called 41414141 because this is what was in the imports entry and we would have crashed. But in this case, you can notice there is no crash and we have a valid pool chunk in the return value. This is because, again, we did not have to do a memory fetch to the imports table. Thus, whatever is in the imports table at the time the image is loaded is what remains, no matter if an attacker corrupts it. So the point in calling this out is one of the known limitations of kernel CFG is protected by retpoline. Obviously, attackers, they can do things like overwrite return addresses. So in this case, I have a thread. This thread is in a suspended state, which effectively means there's an asynchronous procedure call, or APC, queued to it, telling this thread, do nothing. I then use a kernel mode read-write primitive to corrupt one of the return addresses on the stack with a simple ROP gadget. In this case, it just breaks into the debugger for demo purposes. When this thread resumes, the stack will unwind and my ROP gadget is obviously executed because in the red box here, we've broken into the debugger. This is outlined first by a technique called kernel forge, which kind of pioneered this. So we can obviously still overwrite return addresses on the stack. Well, this is exactly where kernel mode CET comes in, as I'm sure you could have guessed. And so return addresses are now protected. And kernel CET is a little bit different than kernel mode CFG in that it's not binary. CFG is binary. It's on or it's off. You need to compile, obviously, for support. But with CET, there's something called audit mode, where you can effectively put your machine in audit mode, and when a control flow protection fault occurs, instead of just the interrupt handler bug checking, it fixes up the shadow stack or other things that's needed. And most importantly, it emits an event tracing for Windows or ETW event that you can get more information about why this CET violation occurred. Again, as I mentioned in the last slide, we also need HVCI. So the region of memory associated where all the kernel mode shadow stacks will reside is still managed by NT. So there are situations where we have kernel mode shadow stacks like interrupt service routines or DPCs, but the most canonical example, I guess you could say, is a thread being created. Anytime you have a thread being created, you have an associated stack. Well, guess what? If you have an associated stack, you now have an associated kernel mode shadow stack. So the common example is a thread is created, new stack is created, then we need to create the shadow stack. We make an inline call to the secure kernel through the secure system call interface that enlightens the secure kernel, hey, here's where we want this new shadow stack allocation to reside, and please mark it as read-only. But then additionally, a special bit, which we'll talk about later, called supervisor shadow stack bit, which is part of an Intel feature called supervisor shadow stack control. As I mentioned, every thread creation needs a shadow stack effectively. Well, if every thread creation needs a shadow stack, that means that every thread creation now results in a call to the secure kernel, which is going to do what? Do a hypercall and incur in VM exit. We don't really want to do that all the time if we don't have to. So there are two caches that are managed by NT, and rest assured, all of the members of this cache have gone through the slow path once, so they are all read-only in the SLAT table for VTL0. And we have two kinds of caches, a per processor cache and a per NUMA node cache. A NUMA node is effectively a grouping of processors associated with a range of memory, is a very gross oversimplification. And so what happens is, if the conditions are right, we send old shadow stacks, which we are done with, to one of these caches. And the reason for this being is threads typically have an ideal processor or ideal NUMA node. Well, allocations typically will be cached on the processor which they were issued from or executed from. Well, the idea here is that if we can cache these shadow stacks on a processor or NUMA node, we may be able to gain performance in the sense of when we go to get a new shadow stack, that memory may already be cached on a given processor, depending on the conditions. So we have two caches, but there is a slow path, and that goes to the secure kernel. So no matter what happens, if we go through the cache or we go through the slow path, the kthread object, which is managed by the kernel for a thread, is updated with a new field called the kernel shadow stack. It contains the address and also some metadata. We have, as we can see here, documented types. We have user thread and kernel thread are the most notable. You may be thinking, why does a user thread need a kernel mode shadow stack? Well, the architecture on Windows, when you do something like a system call as an example, and you transition execution into kernel mode, it's issued on the same thread which issued the system call. And so we don't want to use the stack in user mode to store all this local kernel data, so we switch into a kernel stack. Well, if you have a kernel stack, you now have a kernel shadow stack. And additionally, just for completeness sake, there's something called shadow stack owner data. It's really used for debugging purposes. And the MMPFN, the PFN structure associated with the region of memory of the shadow stack, contains effectively a masked off address of the kthread object which owns the shadow stack. But before we get to that, that's the final stage, the secure kernel has to do a few things. One, as we know, mark it as read-only. And two, it configures what's called a shadow stack token. So a token is used in certain circumstances to validate that a shadow stack is effectively legitimate. And there's also an example of how to switch shadow stacks for supervisor shadow stacks documented by Intel. You have what's called a restore token. The secure kernel is responsible for configuring this. And remember, the shadow stack is read-only in VTL0, so it cannot be modified. The secure kernel has delegated the permission to do this. And on a context switch, special CPU instructions are used when the thread of the new shadow stack is scheduled on the CPU to update the new shadow stack pointer register value and also save the old value for the old thread leaving the processor. Thus, when this old thread is scheduled again, we know where to pull the old shadow stack value from. So that's kind of the canonical example of shadow stack switching for supervisor shadow stacks. And it's also responsible for initializing the return address. What I think is one of the, I said main engineering hurdles, this is just my opinion, is writes to the shadow stack. So this is an interesting thing because putting SLAT and hypervisor aside for a second, it's very easy to disallow ordinary data writes, so a move operation to a shadow stack. All we have to do is know where the shadow stacks are. So there's 4 paging structures typically on Windows. There's something called on Intel processors, there's something called LA57, which is coming in the future to make that 5. But for now, we basically have 4, and these are made up of page table entries. Intel documents special PTE bits set for all of the paging structures used to translate the shadow stack, marking all of them as writable except the final PTE that maps the physical page. It's marked as read-only and marked as dirty. That's a special set of bits that we should not find anywhere else, and thus we know, okay, this is a shadow stack page. But what about with SLAT? Because we're using CET with the hypervisor. And the hypervisor means we're not using the PTEs, we're using the extended PTEs. So number one, how does the hypervisor know what the shadow stack pages are? But number two, if a call pushes a return address onto the stack, and a return address onto the stack goes on a shadow stack that's read-only, that's going to cause an EPT violation because that's a read-only region of memory. What's that going to do? That's going to do a VM exit. We don't want to do a VM exit every single time a call happens in kernel mode. So we use what's called the supervisor shadow stack control feature to help with this. So there's a special supervisor shadow stack bit, which I talked about, set in the EPTEs for VTL0. So NT lets secure kernel know, hey, this is a shadow stack region of memory, and then that is passed on to the hypervisor, and that's where the read-only entry, the read-only permissions and supervisor shadow stack permissions are set. So same thing here, the extended page tables all have page table entries with control bits. All of them are marked as read-write, except the final extended page table entry is marked as read-only and supervisor shadow stack bit. This is how we know this is a supervisor shadow stack. Thus, we can disallow ordinary data writes, but not have to incur the cost of a VM exit every single time a call happens because we know, hey, this is a shadow stack region of memory. And another security benefit we have here is that shadow stack accesses are not allowed to occur to a non-shadow stack page. So an attacker could theoretically take a shadow stack region of memory, remap it to a non-shadow stack that's writable, and forge their own malicious shadow stack. Well, shadow stack accesses cannot happen like that because this supervisor shadow stack control feature says accesses can only happen to pages marked as supervisor shadow stack. So we also gain that. And as far as I'm aware, Windows is the only platform that actually leverages this today. So there are other things, though, that kernel CET needs to be aware of. An exception is an example. So we're executing code in kernel mode, an exception happens. Well, we have to go dispatch the exception handlers. The exception handlers do their thing, and then we have to jump all the way back to where execution was before. Well, the way that that works is there's a special what's called context record and exception records that are used to figure out, okay, here's where we need to go back in execution. Well, now part of the context structure is the shadow stack. So if this was handled by VTL0 exceptions, what's stopping an attacker from being able to coerce the exception handlers to say, actually update the shadow stack pointer to this value? So what we actually do is we delegate updating the shadow stack value from exception to the secure kernel. So the way that this works is there's special MSRs or model-specific registers that are used for context switch, privilege context switch, context privilege switch. So when a processor is running in current privilege level 0, which is kernel mode, and goes to 3, which is user mode, there's a special MSR where it can pick up, here's the intended shadow stack value for the new user shadow stack that I need to maintain. Well, we also have that same functionality for guest to hypervisor. So when an exception happens, we go inline to the secure kernel through a mechanism called shadow stack assist, and we basically say we need to update the shadow stack to this value. What happens is there's a special virtual processor register associated with the virtual machine control structure for VTL0. And the VMCS is configured in a way that when VM entry occurs, that's the context switch back for the processor executing in context of VTL0, it will pull the new shadow stack value from this entry in VMCS. And so for all intents and purposes, only the secure kernel can supply the new shadow stack value for an exception is one of the things that we have to be aware of. But also we have opportunistic checks. So the secure kernel knows about all the executable code in VTL0 through those NAR structures I mentioned earlier. And exceptions are associated with a new context record. So the secure kernel goes, we're already here, we're already updating the shadow stack value. Why not take the instruction pointer from the context record and validate it resides within a known executable region of memory? So that's another opportunistic check which is done. Another interesting note here is that the CPU is going to issue a special interrupt when the control flow protection fault is incurred, but that is not all she wrote. Because what happens here is that on this interrupt handler being invoked, which is a thing which is handled by VTL0, the stack value which caused the CET violation is preserved, and we actually loop over the entire shadow stack. And if the stack value which caused the violation is found anywhere on the shadow stack, we use our assist functionality to fix up the shadow stack, and execution can continue. So you can still overwrite return addresses on the stack as long as the address you're overwriting is also found on the shadow stack still, which is a very interesting note. So what are some of the conclusions here? Well, Kernel CET, it's only been around since Windows 11 22H2, and it is not enabled by default. And so what that means is research surrounding this mitigation, first of all, requires specific hardware, but also requires later versions of Windows. So most of the research which exists today surrounds actually taking advantage of known weaknesses in forwards edge CFI, so taking advantage of kernel CFG. Again, we have the entire bitmap of all valid call targets that we can choose as an example. We also have other things like counterfeit object-oriented programming, jump-oriented programming, where we can still get around kernel CFG. So that's where most of the research exists, and that is because Windows does not leverage indirect branch tracking, which is the other feature of CET, which validates indirect calls and jumps. IBT would mitigate against this, but Windows does not use it. Obviously, kernel CET seems to be the stronger of the two mitigations. It's hardware enforced as well. I think that out-of-context returns could be something that's interesting as well. I've seen it maybe talked about before, but no real public POCs and whatnot, so I think that could be an interesting vector for research. But you can obviously still do remapping. As I talked about earlier, we have the supervisor shadow stack control feature, which can mitigate against this for shadow stacks. But what's stopping an attacker, as an example, for taking a region of memory that's KDP protected and remapping it to a writable page and writing to it? Well, we actually have a mitigation now called Hypervisor Linear Address Translation, or HLAT, which is used through the hypervisor and special CPUs that is available now in 24H2 of Windows that can prevent this remapping, which I've just mentioned. And so I just think that the presence of all these mitigations, when they're all enabled by default, obviously raises the bars for attackers. ROP is completely mitigated effectively with CET. The interrupt handler stuff is obviously a Windows-specific implementation thing. So it'll be fun to see the cat and mouse game which ensues in the future once more companies adopt the newer hardware and CET is fully enabled, HVCI is fully enabled, all of these mitigations enabled in tandem. And so with that, I thank you for coming to my talk. Thank you to the folks in this slide here for answering a lot of my questions. Here's some additional resources. I don't think I'm going to have more than a minute for questions, but I will be in the wrap room afterwards if folks would like to ask anything there. So thank you for coming to my talk, and thank you to Black Hat for having me.